Hi, everybody. I'm Ash Davies.
I'm Bill Phillips.
And this is Demystifying Molecule. So a short introduction about who we are. As I said, I'm Ash Davies. I'm an Android and Kotlin GDE in Berlin, Germany. I'm a senior Android developer at Snap Mobile. And in contrast to Bill's experience of actually writing a book, I once thought about it.
My name is Bill Phillips. I currently work at Cash App. I am an uncredentialed opinionated person. I am a contributor to Molecule. If you've seen the RX to coroutines concept series, I wrote that, so I've put a lot of thought into coroutines going into that. And ages ago, I wrote a book. I don't write that book anymore, but I wrote the first edition, so I still say, hey, I wrote that book.
So this talk sort of started out life as a tweet, actually, from myself. I was starting to play around with the Molecule library in one of my pet projects and sort of fell in love with the idea of using Compose in this way. So I was thinking about how Compose actually runs from a runtime point of view, and why there wasn't any documentation about this or how to build your own compiler. So of course this tweet came out, and of course that's how it started, and this is how it ended up. Bill challenged me into actually making it a talk, and thankfully he's here to help out.
Yeah, I was like, I didn't get a talk accepted, so.
Cool.
So cool, let's dive right into it. So just before we get started into talking about Molecule, let's just talk about some basic ideas with Compose UI. I'm not going to go into a lot of depth, but we do want to have a brief introduction. So Compose UI is really cool, and basically it lets you build your user interface by defining functions. So this function, composable function, login input view, you run it, it's going to create something that looks like that on the screen. The cool thing about Compose UI is that, well, there are a lot of cool things, but the things I want to focus on as a runtime for this talk are this idea of recomposition is one of them. So recomposition is how Composable gets run. So say we have an input Billjings 1, 2, 3, 4, 5. Our initial render, we're going to invoke everything in the body of this composable. But if I decide to change that input to Ash Davies, only the things that are dependent on that input are going to be reevaluated. So we have this labeled text field that takes that as an input. That's going to be invoked, but all the other stuff is not going to be invoked. That's kind of an efficiency optimization that Compose has built into it. The other cool thing that Compose UI has is this notion of snapshot state. So our composable functions, if we think about them at runtime, they're constantly getting reevaluated. So they're in a loop and they're getting run over and over again. And the idea is that each time you invoke them, they represent some state, the current state of what your composable is. But you may have state that you want to persist across invocations of this. So we have this remember function and remember savable and other friends that are all prefixed with remember. And remember things add things to what is called the snapshot state. So I create a mutable state of username, and I get a mutable state object, which then will persist across different invocations, and I can update that with different values over time as well. So we just hook up our labeled text field to that state instead, and if we want to pull out that value when we click that text button, we can just pull it out of the state, and it's going to be whatever labeled text field updated those values to. So that's the basics. Of course, in a real application, we're going to want to get more involved with the kinds of logic that we implement here. So for like a login screen like this, I may want to say that when I tap that login button, that I invoke some web service and I display like a spinner until the web service returns a response. So I can, because of all these tools, hook all this up inside of my composable. I just wire up the username and password. I launch a launched effect. This creates a managed coroutine. And I just invoke the session service and get a response. And there's my screen. Everything is right there. This is, if you've played around with Compose, you've probably written code like this. But in production, it's not ideal. And the big reason why is that you really can't validate anything in this without also validating everything in this. I was thinking about it before the talk. I think of this as like cognitive load, right? Whenever you're writing code, you want to make sure that if you're building a view, you're just thinking about it, what it looks like. If you're modifying the logic behind that view, you just want to think about the logic behind it. Here, you can't actually exercise this thing without doing everything all at the same time. So this is not production quality code.
It's also symptomatic of monolithic code where you don't have these seams, so you can't really test things in between.
Exactly, yeah. So at Cash App, what we've done for many, many years now is we have a simple idea for teasing these two things apart from each other, which is we define an object protocol that lets the view communicate with the business logic that drives the view. So here we define a login UI model, which is pretty simple. We just have loading and content. And we have a login UI event. Usually this would have more than one event. But we're just going to have a submit event here that gives us what username and password were submitted. The important distinction to note here between these is that the UI model is always going to be stateful, right? If I want to display something in the UI, I should be able to, I shouldn't have to do anything more than just give it a single UI model. The UI events, on the other hand, are eventy in the sense that, like, I need to see the whole stream of events to understand what my view is actually doing. So if we do that, our view can be cleaned up a whole lot. All of a sudden, now we just need the model. We display a progress view. If it is loading and if it's content, we display our login input view that has the username, password, all that kind of fun stuff. And then we are free to put the business logic somewhere else. And that's kind of the big question. What do you implement the business logic in?
So this is where we sort of thought about the motivation for building something like this and what it might kind of cause us to produce. So this is an example of the login presenter. Now let's not kind of worry about whether we're using MVP or MVC or whatever architecture. We're just here for a contrived example. This is part of your slide, actually.
Yeah, this is the surprise slide that I threw in there without telling you.
Right. I was wondering why I couldn't recognize the slide, so he decided to surprise me last minute. Thank you very much. It's a real friendly move. So we're using async task here because, well, why not?
Well, this is how we used to do things, right? Like way back in the day when we didn't have any other approaches.
Right, so I caught off guard there. So the idea here was to sort of take a step back and think about how we used to sort of build our architectural applications and how we used to kind of model our domain logic. And we might have used something similar to this, but probably not.
Yeah. I mean, this gives us the ability to manage some work. We have a notion of events with a callback, but it's a very callbacky kind of API. We had to wire everything up by hand. It is not great. So we haven't done things like this for a long time.
I really love the deprecation, suppression, and nullable, mutable public state.
Oh, it doesn't fit on one slide either. Go to the next slide.
Oh, wow. This is going to get worse. You can get worse than this? Oh, wow. Oh, wow. Inner class. Ugh. I'm getting nightmares now. So you can imagine, back in the day when async task before it was deprecated, that you might have done something like this if you hated yourself.
But this is kind of why we started doing things like RxJava, right?
Yeah, let's move on quickly. So fast forward a few years. not enough, into the idea of reactive programming when RxJava became very popular in the Android world. Now, of course, mentioning an RxJava in 2022 might seem a bit ludicrous, but it's good for a bit of a history lesson because it introduced a lot of these paradigms that were previously unknown in our little ecosystem. So the idea of having like reactive pipelines where you would define a sequence of operations to be applied to a given state. So you'd have an input that was sequential and predictable. It gave us a much better tool set for actually managing thread handling. So you could easily handle I/O operations or as necessary, and actually kind of made it a bit easier to consider what to do in case of errors, where errors would be handled inline. You might remember that this do on error operator from RxJava. And ultimately, it gave us a bit more lifecycle awareness. So if you've ever used a disposable or composite disposable, you'll be aware that this had to be cancelled at the end of the Android lifecycle on destroy. So going on from this, I'd like to give a shout out to Jake's talk actually from the same year. It was like 2018?
I think it's 2017, if I remember right.
2017? Yeah, so even 5 years later, it's still kind of relevant to how managing state from different sources can be quite a complex and difficult task. So it's important to kind of think about these complexities and the problem we're trying to solve.
Yeah, this diagram still is it's going to be relevant to all the business logic we ever write. It's kind of the core job that we're doing. We're sticking together different asynchronous sources of information.
Yeah, so thanks, Jake. So if we kind of take the previous wonderful async task example and sort of remap it into the Rx world, you might end up with something like this, where you've got an input observable of events that you're then kind of mapping into this new state. So we're taking a login UI event and producing a login UI model, both being observable. But there's a lot of little caveats here that you might not be aware of if you're not familiar with the RxJava world. Things like this Yoda-style start with syntax, which is wonderful that we're using twice here. So it's first off not so clear which one comes first, but also that it's coming at the end of the statement. So we've got our work happening up top and then, oh, by the way, start with this. It's a little bit, it's not so easy to understand if you're coming to this as a new developer. And not just this, we've got things like two observable and single flat map that were introduced with RxJava 2, making the whole thing a little bit more complex. So there's lots of little kind of gotchas here and foot guns and, as we joked during preparation, face guns.
Yeah, there's a whole learning curve with writing reactive code where you have to first think, what do I want to do? And then think, secondly, how do I accomplish this in the reactive paradigm? Which as you get more familiar with it, you get more fluent with that, but it doesn't solve the original problem, which is that your language for expressing things doesn't really map exactly to what you want to do a lot of times. So I'd like to demonstrate this example as well as kind of an example of how things can go really quite out of hand. I was shocked when Ash told me that this is a real production example.
Yeah, so it might be surprising this is not a contrived example. This is an actual real-world example that I'm not sure, because I've not worked there for a while, but it may still be there to this day. The names have been changed to protect the identity of the source.
Yeah. The thing I do want to point out about this, by the way, is this is not necessarily specific to RxJava. This kind of result is one of the things that comes out of working primarily in the reactive paradigm. So if you write your code mainly reactively, even in something like Flow, you can still end up with code that looks like this that is difficult to understand.
I'd say with a few less two observable calls, but maybe not, depending on your scenario. So, introduction of Kotlin coroutines, where this idea of imperative style syntax sort of kind of took a hold, where instead of having these kind of callbacks or process executions, we've got something that looks a bit more, readable. There should be a background there, yeah. So when Kotlin was introduced, coroutines was introduced, it was introduced as a native library, which gave us a bit of confidence about the longevity and the stability of this feature. And I'd like to kind of take the opportunity to say that Kotlin coroutines is not the same as Kotlin X coroutines. One is a support library and one is a language feature. So you end up with less of these kind of Yoda-style start with syntax, and for a start, even the keyword operator for suspended functions just is awesome.
Yeah. So what does it look like?
What does it look like? Oh yeah, of course, observable will be able to have a flow.
Yeah.
So take the previously contrived example as a coroutine example, and now we just changed it over to having a flow. Now it's a little bit better that we've got things in a bit more of a kind of logical syntax. You can see there's a sequence of operations, and you can understand that, hey, I'm going to emit this first, and then I'm going to do this, and then I'm going to do this. But we still end up in the situation where we've sort of got this flow as a kind of analogous of observable. So it's a bit. It's better, but
yeah. To me, what I love about it is that it solves that core problem of RxJava where I can't write do A, then do B, then do C, then do E, right? That's pretty easy to do in coroutines, but the problem, as we'll see, is that it doesn't really solve that problem that RxJava has of making it really unclear when you're stitching together multiple data sources.
Yeah. So, when you've got multiple data sources coming from, and it's a bit hard to show in a small code sample because this usually happens organically in production code, where you kind of then adding more and more sources to the logical state creation. So here's just a kind of a simple example. You might have managing of the connectivity to influence how your state is actually being created. So one by one, you're adding more things to this. Now it always reminds me of when a product owner first saw the navigation drawer. They just keep on adding one more because, well, you've got unlimited space. And using this combine operator, it makes it a little bit difficult to manage. Now, of course, it works, but it's not so clear, and it's a bit kind of difficult, and it doesn't scale very well.
Yeah, that's the big problem with this, is that as you're organically growing your code base, you just end up throwing in one more thing into your combine. And if you want everything in that combine to have the same view of the data, you're kind of stuck with that. There's not really another option. That's again inherent to working in the reactive paradigm, that dealing with these pipelines of data and what goes in them is kind of the challenge.
Yeah, and I think it obfuscates a lot of behavior that's going on behind the scenes. I mean, combine as an operator, it's just one type of combination. You've got different things where something might not emit at all. And in this example, you can see that each element or each kind of composition of this is given the same sort of priority or the same emphasis, when that might not necessarily be true. So it kind of cuts out the opportunity for early failures or simple returns. So obligation to mention this, Compose is not the same as Compose UI, and Cotty knows it's true, and so do you. This is also my introduction of my cat, Cotty. Yes, he is named exactly after what you think he is, and much like his namesake, he's also grown quite large in the last few months.
Yeah. It's relevant to point this out, though, because we're talking about business logic, right? And we've just pointed out earlier on in the presentation that Compose actually has a lot of stuff that lets you do this business logic, right? The funny thing is you don't actually have to use any of the UI stuff. So is it possible to just throw away the UI part and just have plain old Compose code?
I don't know, is it? Oh, hello, Android.
So yeah, we can consume flows from within Compose. We can have compositional state, right? So I can feed flows one by one into mutable state, and then I can use whatever subset of them I want in dependent code. It's not like that combine situation where I have to throw everything into the combine. And we also have declarative job management with launched effect. So that gives us the ability to control whether a coroutine is running based on some state input. So maybe it will work.
Maybe. Let's see. So, you want to take over?
Yeah, so this is our presenter that we wrote earlier in RxJava and coroutines, written in composable business logic. So this doesn't emit any sort of UI. There's no nodes emitted by this thing. And it does implement the logic that we want. If you run this in your app, it will do the right thing. And I'm not going to get into too much to how this works, because that's kind of, hey, talking about Compose, which you can probably find out about in the documentation or another session. What's that?
Some lovely use of double bangs here.
Yeah. But we do want to talk about, like, So I can write it this way, but then what do I do with it, right? How do we test it? There are Compose test utilities, but they're really more focused at UI. In fact, I don't know anything about them, so I can't speak to them. But I always think from a unit testing standpoint, like how do I validate inputs and outputs? How can I just run this, right? And the Compose runtime doesn't have an easy solution for that. And then there's also the question of how do we fit it into our architecture, our existing architecture, our greenfield architecture. Maybe the answer to these questions is different. Maybe it's the same. We don't know. But we kind of need something that lets us think about running this business logic by itself. At least we did at Cash App because we had a big legacy framework that we were running all this RX Java stuff in, right? We want to plug this stuff into this framework. So we wanted some kind of adapter tool for this.
I think as well, actually, with testing, it's important to remember, or important to observe, that the current test frameworks available for Compose actually are kind of restricted to only UI testing. So to do so, you sort of have to use the Espresso framework and actually often have an Android device or at least an emulator. So unit testing is sort of difficult to achieve. So this is really quite interesting.
Well, it's good to hear that because I don't know anything about that and you do. So I'm glad that I said something that was true. So that's what Molecule is about, is turning compositions into flows. So here's the core idea, observation. Say we define an integers flow here. Just a toy example. This emits 0, and then with a delay, it emits 1, 2, 3, 4, 5. We could also define an integers composable that initially emits 0 and then does the same thing. It has the delay and emits 1, 2, 3, 4, 5. So these, if you think about what the code we've written means, express the same idea, which is an asynchronous stream of values. So that is what Molecule is all about. So the question is, how do we stand up a Compose runtime? So I thought it'd be fun. I'm just going to dive right into the meat of Molecule. This is the
Here comes the fun bit.
Yeah, this is the crown jewels of Molecule, in the inner guts of it. So you start off by creating a recomposer. So the recomposer is the part of a Jetpack Compose that owns this recomposition process. It's running this loop. And because it's running this loop, it needs a coroutine context that loop gets run on.
I thought this was super cool as well, actually, getting used to the Compose environment, that it's so heavily built upon coroutines. And, coroutines being a first-class citizen of the Kotlin world. It's really impressive.
Yeah. Then we need a composition. So we construct a composition to put our composition in. This is what we're going to put our content inside of. And that takes two parameters, an applier and a composition context. The composition context is the recomposer. So we just put that in there, and that will serve as our composition context. The applier, on the other hand, is there for all the UI stuff. So it has callbacks like, add above, add below, all this stuff. And we don't need that. We don't care about it. So we're just going to plug in a no-op applier that doesn't do anything.
This would also be the one responsible for managing things like the DOM if you're working in a web environment or anything that you're going to be using in UI. And for example, Mosaic as well, which is a library for using Compose in terminal applications. Again, thank you, Jake. But this is where you're going to be working on that.
Yep. And then we need to hook up to the recomposer. So we launch a coroutine to run this. So this is going to run while our thing is doing its thing. And then we need to hook up the snapshot state. So the snapshot is where our mutable state lives, and we need to observe the snapshot and invalidate. We need to send notifications whenever we have the snapshot dirtied. So a naive approach would be to just register a global write observer and invoke send apply notifications every single time. That could get called a lot, though. So what we're going to do is we're going to hook up a little rate limiter with a conflated channel and a little coroutine to listen to that conflated channel and send notifications. So if we send to that conflated channel, that will make it so that if I have like 5 come in rapidly, that just conflates down to a single item on that channel. So these unit objects on the channel just represent, hey, send an apply notification.
A little bit similar to stateflow, except without the.
Yeah, if you're not familiar with a conflated channel, it is kind of like stateflow in the sense that you can update it multiple times and get just one result. The difference is that channel, you can consume the item off of it. That's not how stateflow works. So having done that, we set up the content of our composition, and so the meat of that is running that content, which is our composable that we want to produce a flow from, and we get some output value from that, and we just have a callback that we invoke. We under the hood invoke that callback in various ways to support different applications, but basically it's a callback. And then once we're done with all that, we need to clean things up when our job is canceled.
Because we're good citizens.
Yes. So we dispose our composition, dispose our snapshot handle, and that's it. So the way that you kill all this stuff is you just kill the owning, you cancel the owning coroutine, and it all gets torn down. That's molecule. Gold star for us. We just built ourselves a molecule.
High five.
Yeah. All right. So important things to note about this. This composition.set content, for this to recompose, two things have to happen, and these two things can get a little tricky. The first thing is that content must be dirty. So either some snapshot state value that it's dependent on has to be dirty, or some other value that it depends on has to be dirty. If that's not the case, then the recomposer is going to sit there and block and wait for it to be dirtied before moving on. The other thing that has to happen is a frame clock must be ticked. So in Compose UI, we have this choreographer frame clock that is built to, provide a user interface to display on the screen at our, at our frame rate. We also have that here, even though we are not necessarily dealing with the UI and the frame, because that's how Compose works. It's not going to recompose until it gets a frame clock tick. So we do have to make sure that we plug up a frame clock into that coroutine context so that doesn't blow up. It will blow up. Another important thing to note about the dirty versus frame clock is that if you dirty that state, that's a persistent situation. So in other words, it's going to be dirty until I recompose, at which point it will be clean again, right? That's not the case for frame clock. If the recomposer it reaches that point in the loop where it's like, okay, I'm waiting for a frame, and you tick the frame clock, I'm going to recompose. However, if you tick the frame clock before it hits that point, it's not going to recompose. So these two things work differently. The frame clock is tricky and can be a little racy to deal with for that reason.
I think it's quite remarkable, though, that working with Compose and thinking about how wonderful this new technology is, it gives you the idea that this must be so complex underneath. And seeing how actually remarkably simple it is to implement was quite interesting.
I guess, we're programmers. Once we learn something, we forget how complicated it is. So I kind of feel that way about Compose sometimes. But it is awesome. I love it. So the public APIs that Molecule expose are these two. And the difference between them is that Molecule Flow exposes a back-pressured flow of items. It's like a regular plain old cold flow. Launch Molecule, on the other hand, produces a state flow. So usually you're going to want to use Molecule Flow in a testing context where you want to be sure that you get and observe every single thing that comes off of the flow. Usually you're going to want to use Launch Molecule in a prod context where you don't necessarily need everything, you just need the current state. That's what state flow is really good at. It's kind of my pet peeve. I really hate unit testing against state flow for that reason. For testing, we will use Turbine. If you're not familiar with Turbine, it's just a handy tool that handles this job of if I am testing a flow, I kind of need to run the flow in a coroutine and then run my test code in another coroutine. Turbine does a bit more than that, but that's kind of the core reason that it exists. So that's why we're going to use it here.
And if you remember having to test any flows before this was available, it would often involve setting up a really uncomfortable asynchronous channel where you're actually piping these events to it, so you can still continue testing in your main thread, or, well, in a unit test.
So there are pros and cons to defining a flow with composable logic versus defining it as a regular flow. The big advantage that we have seen with using composable flows, quote unquote, is that composable is a state flow. That's what it is. You can always ask a composable what its current state is. It'll just evaluate that function and tell you what the current state is. So that means that if you need a value immediately before you have fired up and done any business logic, you can do that with a composable. You can't do that with a flow. The other big advantage is composable state. That's what I see as the big game changer for us writing code in this tool. Is it lets us solve that combine problem and have this nice launched effect management of jobs. Contrariwise, on flows, if you need to have a defined number of items, if you need a meaning for this flow that is not really contextual, you probably want to use a regular flow. What I mean by the meaning is contextual is that, again, the number of items that are emitted by a composable depends on the number of recompositions that you have. That's just how it works, and that can change how jobs are managed and other outputs and consequences of that flow. By comparison, a regular flow, it really just depends on what dispatcher you run it on. You can get different results with different dispatchers, but for the most part, it means the same thing no matter where you use it. So here's an example to kind of help illustrate how this thing actually can work in practice. And also to talk about the recomposition clock parameter. So as I mentioned before, when you're running a composable, you have to have some sort of clock. So the first clock that we had in Molecule was basically the approach of saying, you know what, we're going to use whatever clock is in the calling context. And we did that because there is in production a calling context clock. There's the Android choreographer clock. So usually that's what you want to use in production. You can use it in test. This looks fine. This does not look fine. We had some test tools that kind of did this under the hood, but to give you an idea of what this is doing, you have to kind of yield at every step to drive the composition, wait for the recomposer to do something, and then trigger that frame. And that's because of that issue that I was talking about before with the frame clock versus the dirtied state. You can't like queue up a frame for compose, unfortunately. So we avoid the context clock approach in test code now. Instead, what we introduced is an alternative clock called immediate. And what immediate does is it's kind of a hacky little clock. But basically, what it does is anytime you ask the immediate clock for a frame, it says, sure, here you go. Here's a frame. We have additional fancy stuff that we do under the hood to support back pressure and that kind of thing. But at its core, that's what the immediate clock is all about, is it's just saying, you know what, for this scenario in unit testing, we'd like to test this without worrying about ticking the clock here, there, or another place.
Conceptually, I think you could compare it to the immediate dispatcher from coroutines, but there is a little bit of difference there with the actual way it's invoked. So this one will give you a frame immediately, right?
Yeah, it will keep the recomposer from getting hung up, is what it will do. So, we also use the immediate frame clock in production when we are we have some compatibility libraries. So say that I want to, inside of my old RxJava presenter, run a molecule presenter. Well, we use the immediate clock in that circumstance. So this is another thing that to note about this. We have some more involved code to work around this, but you do have to initially do like a yield or something to get the runtime to fire up those launched effects. That's one of the downsides of this approach to writing business logic, is that generally speaking, if you modify the state to trigger a launched effect, you have to first do a recomposition to let Compose know that this thing is going to run, and then in a test case, you then have to wait for it to fire up those coroutines. We solved this problem by kind of queuing up the events on a channel, but I didn't have space to show that, so I don't have that here. I'm sorry. And then you write the rest of your test. So once you do that initial setup, everything just kind of works great. So we have a lot of test code in production that works exactly like this.
Yay. So when I started using this and kind of using Compose more in the actual infrastructure and architecture of the application, I started thinking to myself, well, now that everything's becoming more composed, so maybe my UI logic is being prepared in Compose, my UI is being rendered in Compose, my presenters and a lot of my business and domain behavior is going to be in Compose. What sort of role does architecture still play in this now? Because Compose is, it itself is a compositional hierarchy, so it's kind of an architecture. Specifically towards like view models and where do these come into play? So take a standard example of a view model for this. Using mutable state as per the Compose documentation, we're doing something very standard here and what it might look like. We're using coroutines here, so not introduced Compose yet, although we are using a mutable state. So the real problem that the view model was introduced to actually solve was, that of configuration change, which, as you're all here, you probably are already painfully aware of all the complexities that are going on. So theoretically, because Compose has a much simpler lifecycle of recomposition, of entering and exiting the composition, maybe we don't have to worry about this anymore.
Yeah. What does Compose look like in that diagram on the right? Where does it get torn down?
Good question. So the thing is that even if you're running everything in Compose, you're still in the ecosystem of the host environment. So you're still at the behest of Android and at the discretion of whatever is going to kind of kill your activity, because ultimately your activity is the one that starts the composition in the first place. So unfortunately, my hopes were dashed, and this idea wasn't feasible to actually drop the view model. And then, Bill and I got talking, and he proposed the idea that, well, actually, if the purpose of the view model was to persist through orientation change, then actually hosting your compositional domain logic there would actually allow you to kind of ignore this by and large. And that is actually what you can do. So here you can see the view model is sort of being used as just almost like stubbing structure to pass the behavior onto the actual presenter. So it's not actually doing anything itself. It's just simply there as a structural aid. And then in the composition in the UI, we're then calling asking that to review its state. So that's how you can sort of use the existing view model architecture with this new lovely compositional structure.
Yes, to contrast and compare, another alternative that we might choose is not to use Molecule at all and just directly invoke our composable business logic from a composable view. And if we do that, our remembers are going to get torn down on every configuration change is the downside.
So quick highlight here. So Zach and the folks from Slack have been working on this navigation routing library called Circuit.
I have to bring this up because Zach has been pestering me about circuit questions for ages now, and so I would be remiss if I didn't bring it up here.
So not to go too in depth with it because it is still under heavy development, so things are likely to change. But I would definitely recommend checking it out and just keeping an eye on it and seeing where the roadmap goes with that. But as a short example, you can see how the screen is represented as a parcelizable object. and what's going on there with a nested state. And there's a lot more to this. So, you'll have to actually go through the circuit builder and register your factories. And in the sample, there's using DI quite heavily, Dagger quite heavily. But you can see how it's sort of handling this in a sort of routing paradigm that you may already be familiar with if you're using routing from other libraries like Jetpack or Compose Navigation. Another example I'd like to highlight is Decompose. Now, Decompose is a much bigger example, and it covers a lot more use cases from Kotlin multi-platform, but itself does encompass the same sort of similar routing behavior with a child stack, and it has some similarities in a lot of ways. And you can see how this config is passable, which is representation of the screen, and it's creating a child to then have this stack layering of navigation structures. I think it was a tweet from PY a few days ago that he's building his own navigation library with it's just a stack, right?
I think that's what we all want from a navigation library. Could it please just be nothing but an array list representing our back stack? For some reason, this is really the case.
It's Android. Things get complicated.
This is Sam. This is a slide that has my dog Sam on it.
Well, we're both pet lovers, and we thought this was a really good opportunity to introduce you all to our lovely pets. You may have seen the photo of Cotty earlier, I think. And here's my other cat, Pi.
Yeah, our subtle signal that we're winding up the talk.
So all the code examples you've seen here are available at this repository on GitHub. Unfortunately, the cat is not, but you can follow me on Twitter and find lots of cat photos. They love to sleep in positions that, let's say, expose more internal machinery than they should. That's everything.
Thank you very much.